Hello, I'm Taylor, and today we're going to be talking about a solar eclipse, but not the one this last summer. We're going to be talking about the solar eclipse on May 29th in 1919, and why it is considered the most important eclipse in the history of science. Why is it called that, though? Well, it completely overturned hundreds of years of Newtonian physics and helped prove Einstein's general theory of relativity, matter curves space. Newton theorized that space and time was absolute, and that gravity was simply two masses attracting each other. So, what did Einstein believe? Well, Einstein's opposition to Newton's theories on gravity first arose from his theories of special relativity, which state that there is no absolute reference frame, the speed of light is approximately 300 million meters per second, and E equals mc squared, which means that time and space is not always constant, like Newton thought. But then, what about gravity? Einstein had already overturned Newton's theories on the absoluteness of space and time. So how does gravity connect to his theory of special relativity and change from Newton's theories on gravity and space? Questions like these and a decade of work later, Einstein then produced the general theory of relativity in 1915. According to the theory, not only are space and time not absolute, but they are also interwoven to create a four-dimensional space-time, the fabric of the universe. What we perceive as gravity is really matter curving the space-time and other objects following this curve. Eddington, an astronomer, wanted to put the theories to the test. But how would he do it? In order to see the effects of matter's curvature, they couldn't just use a random object. The object had to be extremely large, like the sun. To test if the sun curves space-time, Eddington decided to measure the position of the Hyades cluster, which would be close to the sun's edge at the period of testing. As the speed and position of the cluster in the sky was already known, any discrepancies due to the sun could be tested. According to Newton's theory of gravity, the pull of the sun on the photons of light from the Hyades cluster would cause a displacement of 0.875 arcseconds. According to Einstein, the curved space around the sun would create a displacement of 1.75 arcseconds, a value twice as large as Newton's, but still extremely small and impossible to see with the naked eye. Such small measurements would usually be impossible to see with the sun's glare, which is why Eddington used a solar eclipse and the vastly reduced light to see the usually hidden Hyades cluster by the sun. With a clear plan, during the eclipse in 1919, Eddington and his research team took dozens of data points that found a displacement of 1.75 arcseconds, proving Einstein's theory. Matter really does curve space. This bending of light around massive objects due to their effect on space is now called gravitational lensing and is vital to unveiling the mysteries of our universe.